Okay, so what we're going to do is we're going to apply some of our calculus techniques specifically to just graphs, exponential graphs. And let's see how this goes. All right, so in our very first example, we have this exponential function. And some of the typical questions that you might find that involve some calculus are these, right? Where's the function increasing, decreasing? Concave up, concave down. Where are the vertical, horizontal asymptotes? Where's the max and the min? Where are the points of inflection? Okay, and actually, because these are exponential functions, we really won't see a max or a min or a point of inflection. So we're just going to focus on the first three, and then we'll practice these with some other functions. Okay, so question one, find the intervals where the function is increasing or decreasing. That involves the first derivative. And so we take the first derivative of our function and we get this. And something that we should notice is since e to the x is always positive, that means this function is always going to be positive, which corresponds to an increasing function on its entire domain. So we've got an increasing function here. And this language is fine. Like if you were on a test and it said this was the question, you could actually write this as your answer and then that would score you full points. Since e to the x is greater than 0 on its entire domain, then y prime is positive on its entire domain, thus the function, the original function, is increasing on its entire domain. So that would be satisfactory. Let's take a look at question number 2. Find the intervals where it is concave up or down. That involves the second derivative, and we've found the second derivative here. And again, we've got the same situation that where this is always positive. And so since our second derivative function is always positive, that corresponds to a concave up. Y double prime positive is concave up, so our function y is concave up throughout its domain. All right, so let's take a look at number 3, the horizontal and vertical asymptotes. We'll talk about the vertical asymptote first. Usually we find these by finding a place where our function is undefined, where we have a value of x that yields some sort of impossible situation, and there is none. E to the x is, and all the different variations of e to the x, all right? Any multiple, any addition, subtraction, whatever, multiplication, any multiple of this function is going to be continuous. There is no vertical asymptote. Okay, so we'll move on to the horizontal asymptote. And the way we look at that, the horizontal, we look to see that our function, the graph of our function, sort of levels off at some number. It gets close and close and sort of looks very flat. And so what we do is we look at very large values of x, both positive and negative. So what we're going to do is we're going to look at first what happens when we look at very positive large numbers and substitute it in for x. So if you imagine some large x number here, then e to the x is going to be humongous, then times 2 even more humongous, and this plus 1 doesn't even really matter. What's going to happen is we're going to have a function that goes off into infinity. It gets bigger and bigger and bigger. What happens when we take, and we can't stop here. We only looked at one side of our function. We didn't see if it approaches, levels out on the other side of our function. So we have to look at the other side. So when x approaches negative infinity. So when we look at that, we substitute negative infinity here. We can do a little bit of rearranging. When we see this, we should be thinking this. And of course, e to infinity is going to be infinity. So 2 divided by infinity is going to be 0, right? And now over here, this plus 1 isn't affected. So this is going to 0, but this stays the same. So the net effect overall is that we're getting closer and closer to 1. So there is a horizontal asymptote at y equals 1. Okay, let's take a look at another example, slightly different. We've got a negative up in the exponent. We're going to go through the first three examples. Again, 4 and 5 we're not going to pay attention to. So, where is it increasing? Find the first derivative, and we've got a situation here where we have to sort of evaluate what's going on. Since we know that this portion of it, e to the negative x, is always greater than 0. So remember your graph, it sort of looks like this, right? It's always greater than 0. It's always positive. So a positive number times a negative number, that means this whole function is always going to be negative. So if our first derivative is always negative on its entire domain, that means the original function is always going to be decreasing. So this is a decreasing function on its entire domain. Okay, so where's it concave up, concave down? We're going to go ahead and look at the second derivative here. And we see that we've got a positive times a positive. No matter what x is, this is always going to be positive. So we've got our second derivative is positive. So that means throughout the domain, so that means our function is concave up throughout its domain. Okay, horizontal, vertical asymptotes, again, there is no vertical asymptote. There's no place where this becomes undefined, so no vertical asymptote. So horizontal asymptotes, we have to look at the extreme values of x. Let's start with x is equal to positive infinity. Now notice when you insert positive infinity into here, what we're going to do is we're going to take the opposite of positive infinity and make a negative infinity, which again makes this whole term disappear to 0. So as that disappears to 0, the positive 3 stays there, so we've got y equals 3. So it starts, as we go to the right, as our graph goes to the right, it's going to level out at y equals 3. Let's see what happens, when we approach x, as x goes to negative infinity. Again, when we substitute, that negative infinity changes to positive infinity, so this term turns into positive infinity plus 3. That should be a plus 3, I apologize, but that's still going to be infinity. So when we go, as we look at our graph towards the left, it goes upwards off into infinity. So the net effect is that we still have a horizontal asymptote at y equals 3. All right, here's our final function. This function is one that I invented to be really, really hard to evaluate all these things. This is not the kind of function that you would get for a paper 1 style question, like without a calculator, but we're going to try to approach it as if it were a paper 1 question. So let's try it. So where's it increasing? We take the first derivative and we get something like this. All right, and once again, this is a positive, this is a positive, the sum is going to be positive. So since the derivative function is positive throughout its domain, then the function is increasing on its entire domain. All right, so that one came out easy. Where we're going to run into some problems is with the concave up, concave down. So what we're going to have is we're going to have this function here, okay? And we see that we have the difference of two positive numbers. All right, this is a positive number, this is a positive number. So you have to ask yourself, well, is this subtraction, is this difference going to be positive? Well, if this is larger than this, but we don't know that, maybe it's going to be negative because maybe this is actually larger than this. And then both of these functions are changing in value, so maybe there's going to be portions where this difference is positive and portions where it's negative, so where it changes. And so what we're going to do is we're going to try to see if that is true, if there are portions where it's positive and negative. So what I'm going to do is I'm going to set this and see where it equals 0. Right? Where does the difference equal 0? So that I can then see if by testing some values on either side, whether I get a positive value or a negative value. But so I want to know where this equals 0, where the difference is equal to 0. So I go ahead and I start solving. I go through these steps, and eventually I get to this. All right, 1/3 natural log 1/4. Because I invented this, this didn't come out to be a nice clean number. If this were a true paper 1 question, then definitely this number would be some sort of whole number. Okay, so but this is some sort of fraction. I went ahead and cheated and used a calculator, and I calculated it out to give us an idea of, and it's right around -1/2. Okay, so what I need to do is I know that this function is equal to 0 at that point. I wonder what it looks like when I choose an x value that's to the left of this value. Well, that's what I try here. So what I do is I test an x value, and here's our original function, our original f double prime function. So what I'm going to do is I know that this function is equal to 0 at this point. What if I test a number to the left of that point? So, and I picked a really, 1 would be a really simple, I mean, -1 would have worked, but it doesn't show quite a difference between these two. So I exaggerated it a bit. I said, let's substitute -10 in there. And so I get something like this, which I think is very clear to see that this is sort of a negative number, because this is really small. This is a really small number, and this is a really big number. So small minus big is negative. All right. So I know to the left of this number, f double prime is negative, which I know corresponds to concave down. What's going to happen at, to the right of this function? So I picked 0 because I know that that's going to be super easy. I see that I've got a positive, I've got 4 minus 1, which is a positive number. So all the numbers to the right of x are going to yield some sort of positive value for f double prime. Okay, and so that corresponds to concave up. All right, so it's going to be concave down here, concave up, and by the way, that makes this a point of inflection, because f double prime, where it's equal to 0, changed signs, so that means that this is a point of inflection. Okay, so what am I doing here? Sorry, it looks like I got some repeats. I don't know. Wait, where am I going with? Concave up, down, horizontal, vertical asymptote. Sorry, I forgot about that. I was anxious to show you the graph so you can see what's going on. I'll show you that later. Horizontal, vertical asymptotes. The vertical asymptote is when I find a value for x where this becomes impossible to evaluate. As it turns out, both of these are continuous. The difference of two continuous functions is still continuous. Yes, there's a point where this difference equals 0, but that's fine. 0 is a number. It's not, it doesn't create something that's impossible. Okay, so again, impossible would be like the square root of a negative number, or 1 over if you divide by x or something like that. We don't get into either of those situations here. So this is continuous. There is no vertical asymptote. Horizontal asymptote, let's see. What I need to do is I need to pick really big x values. Let's start off with that. For really big, really big x values makes this really big, and this is really small. So big minus small is big. So it goes off into infinity as the graph goes off to the right. All right, it doesn't level off at all. Now, let's look at really large negative numbers. Okay, and so this becomes negative, so this becomes really small. This becomes positive, so that becomes really big. Small minus big is, well, negative, something very big and negative. Okay, so it actually, as we look at the graph towards the left, it never levels off. It goes down into infinity. All right, so now we can conclude that there is no horizontal asymptote. So here's our graph. It's not very exciting. It looks like the point of inflection is very close to the origin. It's actually slightly to the left, right? We remember it's about negative half, right? So this side is concave down, this side is concave up. It's continually increasing throughout its whole domain. There's no horizontal or vertical asymptotes, and so we have done it. Again, that's an example that's probably beyond what you would ever be expected to do. If you were given something like that,